We're going to go through some revision notes for forces in motion to help you revise. Those of you doing IGCSE, Edexcel, if I've taught you, we've been through most of this, so we'll have a look. So first of all, we did motion graphs. So if it's a distance time graph, the steepness of this distance time graph tells you the speed, and if it's a horizontal line, we know that the object has stopped moving because the distance is not increasing, it's staying at the same distance. And this is a negative gradient, so it would be a negative speed. Okay? So the gradient gives you the speed or the velocity of the object. The straight line means the object is traveling at constant speed, and any curved lines mean the object is accelerating or decelerating. So if you haven't done any curved lines, mostly you'll get straight lines, but if you get curved lines, you need to be able to think in terms of what it says here. Okay? Then you got velocity time graphs. Yeah. The area under velocity time graph we did recently, and the area under velocity time graph gives you the distance because you're multiplying meters per second, which is velocity, by time, which is seconds. So you're basically working out what velocity times time is. And distance or displacement, if you think of the direction as well, distance is speed times time, or displacement is velocity times time. Okay? So if it's going up like this, the area under this part where it's increasing velocity while it's accelerating, yeah, the area underneath this straight line going up to 10 from 0 is an area of a triangle, yeah, so you need to do half the velocity, half the base times the height. So if it's 10 there and 5 here, if it was a rectangle, that means it was going at constant velocity all the time, it would be 10 times 5, which would be 50. Well, you know that's not the full area, it's half of that. And because it's a triangle area, it would be half base times height, or 10 times 5, which is 50, divided by 2, which is the same thing. It's the area of a triangle. So this area here would be 25 meters. So you've got to be able to work out that the area under the graph is displacement, and the gradient of velocity time graph is you're dividing this y-axis, velocity, which is meters per second, by time. So you're dividing meters per second by another second, so it's meters per second, which means how much you're speeding up per second. So it's meters per second squared, so this isn't a constant acceleration. Here the velocity is constant, yeah? Here the acceleration is not as fast as it was in the first line, but the velocity is still increasing, and then a negative gradient means a deceleration. Okay? So that's what it says here. You can stop the video, make the notes as you need to, and make sure you got a complete set of notes in your own book. Okay? So then we did forces, and resultant forces is when you've got to take into account that there may be a forward force which is 300, and here the reverse force, the force acting against the motion, is 500. So this shows that the force in the backward direction or against the motion of the vehicle is greater, so it means that it's decelerating, yeah, because the drive force or the thrust of the engine is smaller than the resistive forces, which could be due to drag. Okay, so you can add forces using this method because they're vectors, so the direction matters. This is in the positive direction and this is in the negative direction, or vice versa. Okay, but in either way you can work out that it's decelerating. Okay, so different types of forces include air resistance, which is also called drag, friction, which would be, for example, when you put your brakes on in the car, it slows the car down through disc pads on each wheel, which kind of heat up when you put your foot on the brake pedal. Weight, which is the force due to gravity. If they ask you what is the force that's pulling something down, you mustn't put gravity. You've got to actually always call it weight. Weight is measured in newtons. Gravity is the rate of acceleration due to gravity. So G is more like an acceleration. So you've got to make sure you use weight if you're talking about force. Drag we talked about. Upthrust is when you're floating, or the buoyancy force. So when you're displacing a certain volume of water, it will give you an upward push in normally a liquid, but it can also be true in a gas, although it will be much less because the size of the upthrust depends on the density of the fluid that you're talking about. And reaction is normally a contact force with a solid object. Okay. Now, here is talking about when two objects exert forces on each other. The forces are opposite but equal, and this is talking about Newton's third law. Okay. Now, you can stop the video and make sure you've read every bit of it. And when we have unbalanced forces, like we did over here, the 500 is greater than 300, so you can see the car's trying to move forwards, but the drag force is bigger, so it's going to decelerate. And then to work out the acceleration or the deceleration, and a negative acceleration we also call a deceleration, you use the equation force equals mass times acceleration, which is Newton's second law of motion, okay, when the forces are unbalanced, as in the case given here. So you put the numbers in here. If you know the mass of the vehicle, you can work out the acceleration, okay? So, and then weight is a special case of mass times acceleration, whereas the acceleration due to gravity, okay? So that would be mass times g, yeah, which in GCSE for the Edexcel exam you can use as 10 newtons per kilogram, or 10 meters per second squared. Okay, so I hope you found that useful. A quick revision of balanced forces, unbalanced forces, and different types of forces. You also need to know how to draw force diagrams. Okay. Braking. So when you put the brakes on, the car's kinetic energy will decrease. So the car has kinetic energy due to its motion, and there is friction between the tires and the roads, which generates heat energy. But braking is an active use of friction in the braking system of the car, which uses these days disc pads rubbing against a disc which is connected to each of the wheels, and they slow down the car due to friction. The faster the car is traveling, the greater the braking force needed to stop in a certain distance, it says. Okay. Actually, if you double the speed of the car, it will quadruple the braking distance, because kinetic energy is half mv squared, if you remember your equations. When the car brakes, work is done against the kinetic energy, and hence it decreases. But you can see the braking distance here is the blue part of this graph. You can see when it goes from 20 miles per hour to 40 miles per hour, the blue line hasn't just doubled, it's actually quadrupled. And that's because the energy of the car, each time you double the speed, is actually quadrupled, okay? Because kinetic energy is equal to half mv squared, which you may or may not have met, yeah? So the blue bit, which is braking distance, increases as a curve, yeah? Each time you double the distance, you will quadruple the size of the braking distance. And thinking distance is a time it takes you to react to the need for braking. So it's a human reaction time. This goes up as a straight line. Can you see? The red part of this graph is the increase, which is gradual, and it's directly proportional to the speed of the car. Okay? So you need to know what thinking distance is and what braking distance is, and the stopping distance in total is the distance you travel while you're reacting or while you're thinking about braking. And obviously, the faster the driver reacts, the less thinking distance will be before he puts the brakes on. And factors that affect your reaction timing, could be drugs, alcohol use, the speed of the car itself, which I talked about, and also the mass of the car. A more massive car, that's more to do with the braking, sorry. The mass of the car will affect how much braking power you need, because obviously a bigger mass car also has more kinetic energy for the same speed. Okay, so the braking distance is the distance traveled once the car brakes have already applied, and the thinking distance is the distance traveled by the car while the driver is reacting, or before he actually hits the brakes. Hope that makes sense. And then we did falling and terminal velocity. We had a graph very similar to this. When you jump out of an aircraft, before you put your parachute on, the only thing that's accelerating you is acceleration due to gravity. Yeah. But as your speed builds up, the air resistance, the drag force against you, increases in proportion to your velocity, and eventually it will reach and it will balance your weight. The weight does not change. Yeah, even when your parachute's open, your weight stays constant, but the drag force can vary and does vary according to your speed. So eventually the drag force will become equal to the weight downwards, and this is where it cannot speed up anymore. So this is the terminal velocity is reached without the parachute. Then when you open the parachute, suddenly you're going to decelerate, because actually the drag force momentarily as you open it becomes much greater than the weight. The weight, remember, does not change because you're the same size as you're falling through the air, but you can, by suddenly going from air resistance due to the human body to a much wider surface area which the parachute provides, at that speed will be a much greater air resistance which is produced. So suddenly it decelerates. Yeah, it feels like you're going, that the force is acting against you, that you're going upwards, but you're not. You're still falling down towards the ground. And eventually then, as you slow down due to the parachute, there will come a time where the forces become equal again, and the drag force of the parachute will equal the weight, but at a much lower velocity than the terminal velocity without the parachute open. So this is a very typical graph that you need to be aware of when you do exam questions. And then at this velocity you can land safely and your legs can handle the contact with the earth once your parachute is open. So hopefully what's written here is the same as what I've just explained to you, and this is the kind of language you need to explain things in a GCSE exam. Okay, so they got a couple of questions for you to think about here. What would the weight of the parachutist be if he weighed 70 kilograms? So they're just trying to make you remember that weight is mass in kilograms times gravity on Earth is 10. So you multiply the 70 by 10 and his weight would be 700 newtons. So you multiply the mass by 10 for Earth. And then it says at terminal velocity, what would the value of the resistance forces be? Yeah. And at terminal velocity, the resistance forces, for example here, the force upwards will be equal to the weight downwards, so it'll be exactly the same as your weight. Yeah, and that's the same here. The resistive forces must be equal to your weight. Yeah, so it'll be 700 newtons, but over here it happens at a lower speed. So it's exactly the same as the parachutist's weight. And then over here they've got another question for you to think about. Why does a van that has the same sized engine and that is the same mass have a lower terminal velocity than a car? Well, they're trying to get you to think about the shape of a van, and the car is usually more aerodynamic than a van which has a much bigger surface area which is acting, or the wind can act against. So the air resistance will be greater for a van than for a car. And cars are designed to be fuel efficient, so they've designed them to be more aerodynamic. Vans need to be the shape for carrying objects, so the speed is not the most important factor in their design. Okay, you then should have done springs, and this is Hooke's law. So you can squash springs, that's compression. or you can stretch springs and they have a stiffness constant. Yeah, so if you plot force against extension, the gradient of the force against extension is the stiffness constant for the spring, and that's what the Hooke's law says. It would be F equals kx. So F equals k, the stiffness of the spring, Hooke's law, and extension is normally given as x. Okay, so the gradient gives you the strength of the spring, how stiff it is. It says, how would the graph look if the limit of proportionality was reached? So if you go beyond the limit of proportionality, proportionality means a straight line graph, and direct proportion means that it goes through the origin. That means if you double the force, you double the extension. And remember, we're talking about extension, which is how much it gets longer, not length. Okay, so if you get to a point where you've gone beyond the proportionality limit, that means you're damaging the spring potentially, and it will start to curve. Okay, so that's the answer to this question. And then it says a spring has a spring constant of 25 newtons per meter. That means the gradient over here would have been 25 newtons per meter. How much force is needed to extend the spring by 10 centimeters? So 10 centimeters, remember, you've got to change it into meters because this is in 25 newtons per meter. So if you want to know the force is F equals kx. Okay, so Hooke's law is force applied, yeah, will be the spring constant. So here will be 25 newtons multiplied by the extension, which you need to change from centimeters into meters, and that will give you 25 times 0.1, which means the force applied is 2.5 newtons. Hope that makes sense. This is in newtons. Spring constant is newtons per meter. Sometimes could be newtons per centimeter, but usually in science we use newtons per meter. And the extension, when you're multiplying this equation, you need to change it into meters. Okay? So the spring constant is a measure of how stiff it is. The stiffer the spring, the more difficult it is to stretch it, and the larger the constant value will be. Yeah? So if you had two different springs and you plot them on the same graph, the stiffer one would be steeper on the force against extension graph. Okay? So the extension is the total length of the spring after you've stretched it minus the original length of the spring. Okay? Okay, force is applied to an object that can cause it to stretch or squash. It changes shape. Okay, so this is a materials part of forces. The same graph can be used, you can get the same shape graph if you're stretching a wire. So a long, thin wire, for example, a copper wire, can be stretched in the same way, and it obeys the same proportionality law, that the force you apply will stretch it, and it depends on the thickness of the wire what the stiffness of the wire will be. So that's something also you've got to think about. Okay, so you could say a metal wire is like an elastic spring, and it says an elastic object is one which can return to its original shape or its original length once the force applied is removed. That's only true if you don't damage it in the process. If you go beyond the elastic limit, it may never return to its original shape. Okay? And you've done the work on the spring to change its shape, and while it's stretched or squashed, the spring contains elastic potential energy. Okay? Now this is a useful sheet which involves work done, energy, gravitational potential energy, and kinetic energy. The only one I want to concentrate on is the kinetic energy of a moving object, which I told you before for today's video. The kinetic energy of a moving object, like a moving car, I told you if you double the velocity, the energy of it is kinetic energy of it, which is often written EK to stand for energy, kinetic, measured in joules, is half times the mass of the vehicle or the object that's moving. We were talking about the car, multiplied by its speed squared. That should be a little 2 above the v. Okay, so this is a very useful one when we're talking about braking and braking distance. It's because if you double the speed, the energy of the car becomes 4 times as large. That's why the braking power required will be not double, but 4 times as much, because when you're braking, you're working by applying a frictional force against the motion of the vehicle in the brakes. And the work done here will be the loss of kinetic energy. We're not going to go through the other ones. I'll do a separate video when we do the work on energy. So going back, we are things that we did were stretching a spring, squashing a spring, Hooke's law, terminal velocity. That graph is very important, and think about it, the area under this graph is also the distance that the parachutist falls, but because it's a curve, you would have to estimate it. It won't be so easy, hasn't got straight line bits, but they could give you a question about working out what's the distance underneath the velocity time graph. And if you remember what we did before, the distance under a velocity time graph is always the distance traveled. Forces and braking we talked about. This is why I was telling you, if the kinetic energy is linked to the speed squared, that's why each time you double from 20 to 40, yeah, for example, or from 30 to 60, the blue line doesn't just double, it actually quadruples, the blue part of the bar chart. Okay, so we did forces and braking, and we did different types of forces and how you draw force diagrams, and the size of the arrow normally is increased by length when you're doing it for your exam. You've got to draw, when they ask you to draw like balance forces, you need to make sure that the forces which are balancing each other are of equal length and in opposite directions. Okay, and that's what we talked about, the motion graphs to start with. So I hope you found this video useful. If you did, please give us a like. Share the video with your friends doing it in your own school or in other schools where they would find it useful, and then more videos will follow. And if you want to know when the next video is uploaded, you have to make sure that you've subscribed. Thanks for watching. Bye for now. See you hopefully in the next video.